be discussing microwave energy systems, and I'd like to introduce Dr. David Iannitti to enlighten us on this issue.
All right, cool. Thanks. Well, good afternoon, good morning, everybody. And I want to thank Pascal and Steve Schweisberg for inviting me to speak here today. And I'm certainly going to talk about a topic that's near and dear to my heart. All of this, electrical physics, is certainly near and dear to my heart, but we're going to take the next step, which is microwave energy. I do have a few disclosures here, as you can see listed here, and this is not reflected in the printed SAGES book, so I wanted to be very clear and upfront about that. And as mentioned, I'm at Carolina's Medical Center in Charlotte, North Carolina. Now, we've been talking about some technologies for tissue ablation, and there's a variety of ways of destroying tissue. And I'm going to focus on coagulative necrosis, as you see here in the right lower hand corner. We have radiofrequency energy that Dr. Futzberger has discussed, laser, HIFU, again, and other topics. And I'm going to focus here on one ablative modality, which is microwave. Now, again, we talked about monopolar radiofrequency systems. And there are just two main systems here, and I'm not going to rehash all of this, but you have systems that use a deployable array, and then you have another type of system that uses internally cooled electrodes to deliver energy and create thermocoagulation zones. Now, there's certainly some limitations in the monopolar radiofrequency systems that Dr. Futzberger had mentioned, particularly with electrical and thermal sinks. Inconsistencies in current concentration, so you have inconsistencies in energy delivery and thermocoagulation. And I think that one way to overcome those issues is to use the use of bipolar radiofrequency ablation devices for tumor ablation. And clearly it makes much more sense from a physics point of view to use a bipolar device for tissue ablation than it does a monopolar device. Again, these aren't very common out there in the United States, and only a handful of centers are using them in low volume. So when we look at the electromagnetic spectrum, we look down here on the lower bar. This is the radiofrequency spectrum. And when we're talking about radiofrequency energy for tissue ablation, we're talking about a frequency of about 460 to 480 kilohertz. When we get into the microwave range, we're at much higher frequencies, and we're anywhere from about 915 megahertz up to 9.2 gigahertz. So significantly different frequencies that we're talking about. And the middle one is 2.45 gigahertz, and these three frequencies are clinically used for tissue ablation. Now, in the United States, this was the first available microwave system for human use, and this was a Vivant system. Each of these boxes are individual microwave generators, and you can see coax cable coming off of each. Now, there is only two settings on the microwave generators. There's power, how much power do you put out, and how long do you deploy power. There is no feedback control. Some systems may have temperature feedback, but there is no feedback control with these systems. This is just sending out energy. Fortunately, I've had the fortune of being able to use microwave clinically since 2003, and we've developed a fairly significant experience. Now, back in these old generators, there were no cooling pumps available. The maximum power output for each generator was 60 watts, and you set your time at 1-minute increments. Now, this was the first commercially available microwave system in the United States. This is a 915 megahertz system. You can see it's the same platform as the older system, or the prototype systems. These are capped off at 45 watts, and I'll explain why. And the power settings are set to 1-minute increments with a maximum of 10 minutes. Again, we'll explain that as well. Now, these systems usually come in a 3-box cluster with an additional cooling pump. Oh, excuse me. Now, those are the generators, and we need to deliver microwave to the tissues. So we create microwaves, and there are a variety of ways of making microwaves. You can do it through wave tubes, you can do it through magnetrons, you can do it through solid-state circuitry, and they all have their advantages and disadvantages. And then those microwaves need to travel usually down a coaxial cable, like you would for your cable TV, and then out to an antenna. And there are a variety of antenna designs. The most simple would be a monopole antenna. The 915 system has a dipole antenna. There are tripole antennas. And there's really fun, interesting physics that are associated with antenna design. And if anybody's into microwave physics, all the action is in antenna design. It's the crazy fun part. Now, as we talked about with monopolar radiofrequency ablation, that this is an electrical circuit. You're actually passing an electrode or an active electrode into the tissue. You're passing current through the patient or through the tissue and to a dispersive electrode or electrodes to complete the circuit. With microwave, there is no current passing through a patient. You place an antenna into tissue, you create your microwave, send it down the coax, then the antenna broadcasts the energy. So there is no electric current passing through the tissue. Now, we did mention that we talk about this as monopolar radiofrequency ablation, and then somebody hinted, well, it's technically bipolar radiofrequency ablation if you consider the whole thing a circuit. And I'll go as far as to call those electrodes antenna, but we'll save that one for a little bit later. So how does radiofrequency and microwave work? Well, Dr. Monroe talked about how radiofrequency energy works, is that you have alternating current passing through tissues, which vibrate the ions within the dense current concentration to generate heat. So it's a mechanical heat that's generated. Well, microwave also creates mechanical heat, but in a bit of a different way. So within the near field of the microwave field, and I'll explain that also in a moment, you have microwaves passing through the tissue, which have different magnetic polarity. So the different magnetic waves that are passing through the tissue affect dipole molecules, and the most common one we have in our bodies is water. So the water molecules alternate back and forth with the alternation of the magnetic waves that are passing through the tissues, anywhere from 1 billion to 9 billion times per second. So you can see that we can generate tremendous amounts of heat by passing waves through tissues. So I'm going to ask everybody a question, and I don't know if I can do this or not, but I'm going to do it anyway. We're talking about the radiofrequency magnetic spectrum here. And we talked that down at 460 to 480 kilohertz, we're passing electrons through tissue. However, when we go up the frequency spectrum, we're passing waves through tissue. But it should all be the same, right? This is all electromagnetic energy. So why is one electrons and why is one waves? Can anybody in the room answer that question? All right, well, it's actually very simple. It comes down to the ratio of the wavelength to the ratio of the size of the antenna. So if you look down on the radiofrequency end of the spectrum, and when you're at 460, 480 kilohertz, well below the AM frequency, you're talking about wavelengths in a vacuum. You can see there is probably about 100 meters. So we get to the real world, 1,000 meters. So we get to the real world, maybe it's 300-meter wavelength. These are huge, long wavelengths. And our antenna are only, this big? 3.5 centimeters for a deployable array radio frequency? So you can see that they're completely out of proportion, and therefore the energy is going to be distributed through current. When you look at an AM radio antenna, you see those antennas, they're several hundred feet high. Well, now they're matching the same frequencies to the wavelength, and that's why when they're broadcasting AM radio waves, it's traveling as waves because the antenna is matched to the frequency. Now, when we get to microwave, it's the same thing. We create microwaves, and our antenna are generally matched to the size of the frequency. So again, those numbers aren't accurate because those are wavelengths in a vacuum. So when we look at, say, 915 megahertz in human tissue, the wavelength is about 7.4 centimeters. And so when we have an antenna, it's half of that, so 3.7 centimeter active tip antenna. When you get a 245, the active tip of the antenna is about 1.5 centimeters. So again, now you've matched your antenna to your wavelength, and that allows you to transmit waves. And that's why the coaxial cable can also transmit waves, and it's not transmitting current because the length of the cable is significantly longer than the wavelength. So the waves are going to travel down the antenna, not down the coax, not current. That make sense? So this is great stuff, by the way. I love it. I'm so glad I was asked to talk about this. So let's get to more practical things. Well, when we started with this, and we were one of the first people to clinically use microwave in the United States, we needed to do some safety profiles and look at some time wattage power curves. And so we did in our lab 420 liver ablations and 370 kidney ablations using a 915 megahertz microwave system. I'm sorry that the colors don't match up, but basically what we found here is you can see the time and the power curves that we were sort of clinically using 40 to 45 watts for no really good reason, and we've basically peaked out at around 10 minutes to give you. Once you get past 10 minutes, then sort of the size of the ablation sort of flattened out. So when you look at the optimal settings, you can do a bunch of ablations, and ideally what we wanted is the lowest wattage in the shortest period of time, because we're a bunch of surgeons, we're all impatient, to give you the largest volume of ablation. When you do your fancy statistics, demonstrated that 45 watts for 10 minutes gave you the most efficient ablation. And fortunately, that's what we've been using clinically. And that's why, let me backtrack, that's why the current commercial generators are capped off at 45 watts, because above that, there's really no advantage. You get too much power and you get desiccation around the antenna, and there's really no reason that the generators should run continuously for more than 10 minutes. So those are there for safety reasons. Now, there are other generators out there. This is the second most common generator used in the United States. This is a 2.45 gigahertz system, so different frequency. You can see there's a variety of antenna designs. This is the original antenna, 5-millimeter antenna. This is a monopole antenna. This is a 1.8-millimeter antenna, which was just FDA approved this past year, and this is an end-fire antenna here. This is another system. This is a 915 megahertz system. This is a 4-channel output, and they synchronize the microwaves based on cable length specificity, in an attempt to create larger volumes of ablation with a lower amount of power because you're synchronizing the antenna wave output. And then this is a 9.2 gigahertz microwave antenna. I don't know how many there are in the United States. This is in our lab with an end-fire antenna. And in the UK as well as Australia, there's very, very limited use of 9.2 gigahertz. So we're talking 9.2 gigahertz, 245 gigahertz, 915 megahertz. Well, what's the difference? Well, if you think about it, the lower the frequency, the more depth of penetration that you're going to have. So again, think about a radio. We can sit here in this room and turn on an FM radio, and we'll have a signal. But when we go to, say, Sirius or XM, and I have no disclosures with either of those companies, we don't get a signal because that frequency it's in the microwave range. So it's around 2 to 3 gigahertz. So again, we don't get penetration through the wall, so that's why you don't pick up a Sirius signal inside of a building. Your antenna has to be outside. So we have greater depth of penetration with the lower frequencies. However, for the same amount of power, even though with the higher frequencies we get less depth of penetration, we have higher energy density within that field for the same amount of power. So this is just a quick video of looking at a 9.2 gigahertz. We're just putting an end fire, and boom, you can see that it delivers a tremendous amount of power very quickly in just a few millimeters, and you can see the liver explode. Now we basically just pulled just exposed the antenna, so this would be a monopolar antenna, and you can see here that the wavelength here is about 3 millimeters, so you see a very intense concentration here of energy. This actually is just conductive heat, and for some reason it stopped, and then you'll have some conductive heating along this unexposed internal conductor. Now, we did some clinical work looking at the differences between 915 and 245 gigahertz, and unfortunately we have both systems commercially available that we use clinically, and we've demonstrated for a specific size of tumor that we are able to destroy lesions in a shorter period of time at 245 gigahertz than 915 megahertz. But you can say, well, you're comparing apples and oranges. That doesn't really make sense because you have a generator at 245 that'll put out 100 watts, and you're probably putting about 95 watts out at the tip, where if you have a 45-watt generator with a single antenna, you have a much more power loss along that line, so you're probably putting about maybe 30 watts off at the antenna tip. But when you cluster 3 antennae together, we normalize everything to about 100 watts, so you're trying to compare more apples to apples, you can see for the same size lesions, it takes about half the time for the same amount of power to use 245 than 915 because you're putting twice the amount of energy in because it's twice the frequency at the same amount of power. So, very simple physics. Now, fun physics time. So, there are a couple of different opinions out there regarding how microwave works in the systems. And there's some engineers that use the 1 over d squared ratio. So if you have a distance from the antenna, then the power falls off at 1 over d squared. Well, that doesn't really correlate with what we see clinically. So if you think about throwing a pebble in a pond and you have waves radiating outwards, it doesn't really work like that. You have 3 main types of areas around microwave, and we're talking about near-field microwave physics. You have the quasi-static zone right next to the antenna. Then you have this induction zone, which we clinically call the near field. And then out here you have the planar zone where the waves trickle off. And in the induction zone, the power energy, the energy within that field is pretty much homogeneous until you transition over to the planar zone or the Fraunhofer region. And that, at this point, is where the energy falls off at 1 over d squared. That clinically is important because what we observed clinically is that within the near field, you have a very homogeneous energy deposition within the tissues, and then it falls off. And those are the different sort of fall-off zones that you can see between 915 and 245. So we wanted to really prove this as best we can, and you can calculate this all out mathematically where that transition zone between the near field and far field is, and it does correlate with what we see clinically. And when we learned early on is that in microwave, if we put power Doppler or color Doppler onto the microwave field, we see a very homogeneous, very spherical ball of energy, and then when you shut the power off, the ball goes away, you turn it back on, it instantly comes back on. And we felt that this correlates with the near-field microwave. So we tried to study this somewhat scientifically in the lab. We've presented this at HPBA. We submitted our paper, which is accepted. And we've demonstrated that what we do see on Doppler does correlate clinically to the microwave near-field. We've also tried to do was thermal mapping. You see our very high-tech lab. Again, not a perfect model here, but we have gel with the antenna underwater with a thermal paper, and then we're applying energy to the system. And you can see here that you get a fairly quick homogeneous energy deposition. Now you'll start getting some conductive heating irregularities and some convection currents, which sort of throw it off a little bit, but pretty homogeneous heating of the tissues or the thermal paper with microwave. Now there are 3 ways to heat up tissue. There's conduction, which means that if you put your hand on a hot surface, that heat will be transferred to you. There's convection, which means you're using a current, whether it be an air current or a liquid current, to either move heat or exchange heat. And then there's radiation, and I'm not talking about non-ionizing radiation. So when we talk about near-field microwave, we're talking about radiation. It's like facing the sun. Your face warms up because of radiation, non-ionizing radiation. And if you want to thaw out a turkey as fast as you can, what would be the most efficient way to do it? It would be through convection, right? So you just run a turkey under cold water and it'll thaw out rather than sitting in a fridge for 3 days. Now, when you put a microwave antenna into tissue, okay, all of a sudden the tissue becomes part of the antenna because the antenna needs the surrounding tissue to induce the microwave field. And as the waves are coming down the coaxial cable, they'll then go through a ceramic tip. And so there's really ceramic is invisible to a microwave. Then it'll hit the tissue. And when it hits the tissue, there's going to be a change in the permittivity that will reflect the energy. Some energy will be reflected back, go back up the cable, and other energy will go forward. And so to demonstrate this, this is a 9.2 gigahertz antenna. You can see when I apply power, the reflected energy is fairly low. It's only a 3 millimeter wavelength. You put a metal covering over that with ceramic on the inside, and you can see that the reflected power is up. But as you slide that metal off, then you can see that the amount of reflected energy is going to fall back. So this is great stuff. This is physics in action right here. So there's the fellow burning his fingers. I'm glad there's no sound because I'm yelling at him the whole time to just grab it and stop being a baby. But you can see as you slide the metal casing on and off, you'll see the changes in reflected energy. So that's important because the generators have safety mechanisms built in, and if there's too much reflected energy, the generators will kick off. So what happens is when you put an antenna into tissue, based on the frequency of the energy and the antenna configuration will dictate the size of the microwave field or the microwave near field, which we use for tissue ablation. Now, as you apply energy into that volume, and that volume is going to be fixed based on the frequency and antenna configuration, you're going to deliver more and more power or more energy into that volume. And so the more power you put in there, the higher the temperature. But it's going to be homogeneously heating. And at 915 megahertz, you can get that ball up to about 100 degrees. At 245, you get it up to about 150 degrees Celsius. And then when you're done applying your power, then through conductive heating, that thermal mass is going to radiate outwards through conductive heating of the tissues to give you a final zone of thermocoagulation. Now, Dr. Fusser talked about the heat sink, And I have to be a little bit more specific about what this means. And there's two types of sinks that you need to be aware of. One is the electrical sink, and the other is the thermal sink. And I think we confuse these two terms. So let me quickly explain. Now, remember we talked about electricity. Always seeks ground, and it always likes to take the path of least resistance. So if you have an electrode here, and you have a blood vessel here, and this is all tissue, then the electrical impedance of that vessel, particularly with flowing blood in it, is going to be 10 times less than that of the surrounding tissue. So if this is a monopolar system, then the current is going to selectively go down that blood vessel, and so that means that you're going to not have thermocoagulation on the opposite side of that vessel. Okay? That is the huge disadvantage to radiofrequency ablation, particularly with deployable arrays. Now, when you go with microwave, if you put an applicator into a tissue and you have a vessel or whatever, bioduct, it doesn't matter, you're going to have a fixed microwave field. And then once you apply energy, you're going to have homogeneous energy deposition throughout that microwave field. So it doesn't matter if there's a vessel in there. It doesn't matter if there's air in there. It's still going to go through everything. And so you'll have a much more homogeneous zone of ablation. And then what happens finally is that you're going to have this volume of homogeneously heated tissue. Then again, as I mentioned, through conductive heating, you'll further heat the surrounding tissues. And it's those surrounding tissues that are susceptible to a thermal sink, since the tissue is like a big, the liver is like a big radiator, and you have blood flow going through it, and it's going to take that heat away. And so that surrounding tissue is susceptible to a thermal sink. Do I have any time left? No. Okay. I was going to talk about some complications. Here they are. I've pretty much created all of them, and I can talk about it a little bit more when we're down in the lab. But thank you very much for the opportunity to present this work. It's great stuff. Thank you.